is the relationship between solutions of AX equals B and solutions of AX equals 0. Okay. So this was kind of the relationship you were coming up with in questions 3 through 6 of today's activity. So here on the screen I have your group's matrix. And your image vector was, what was it, 1, negative 2, or something like that? Oops.
Yes.
So let me scribble that down. 1, negative 2. And there it is. Okay. By the way, notice something happens on the left to my solution vectors x. Right now, if I'm choosing a b that's out here, what can I say about the solution to this system? So if I had, I don't know, negative 1 as my right-hand side vector, what does the solution set to that equation look like? It's an empty set. So this is what kind of a system? What word do we attach to that when the solution set is empty? Inconsistent. So this right now is an inconsistent system. But if I just happen to choose a b, a vector on the right here, which is just right, and it's tricky to do, especially with an iPad stylus, apparently. There we go. All of a sudden, this is so frustrating. There we go. There. All of a sudden, the system becomes consistent. All of a sudden, we get a vector over here on the left that solves this system of equations. This particular one happens to be negative 19 over 8, negative 3 over 4. That probably wasn't one of the ones that you found in your group, but it works. I mean, we can check it. Multiply this matrix by negative 19 eighths, negative 3 fourths. We're going to get 1, negative 2. So that works for the b vector 1, negative 2. But, you know, if we choose other vectors, we probably aren't going to get a consistent system. But there's one vector that we can choose on the right-hand side that, regardless of what our matrix is, will always give us a consistent system. It's the 0 vector. How do we know that the solution to AX equals 0 is always consistent? Man, this is bugging me. Try to do it with a slightly less clumsy instrument here. Still not easy. There. So how do we know that AX equals 0 is always a consistent system of equations? Why is it reasonable that this equation always has at least one solution? What vector do we know we can always put for x that will make this work, regardless of what the matrix is? 0. Why? Because when you multiply a matrix by 0, the 0 vector, we're getting the linear combination of the columns of A, which is 0 times the first column plus 0 times the second column. If A has more columns and there are more entries in the 0 vector, then we keep doing that with the columns of A. But certainly, regardless of what our matrix happens to be, this linear combination is always going to give me 0, 0. So the point of that is that AX equals 0 is always consistent. Right? It's never an inconsistent system because the 0 vector always works. And that's significant. X equals 0, and when I write 0 with a vector symbol over it, that means a vector that has all zeros in it. X equals 0 always works. But then the question that I posed to your group was, in question number 2, a question of, are there other solutions to AX equals 0? In the case of your, I think it was a 4x3 matrix or something that you were working with. But maybe let's think of our 2x2 example up here. Are there other solutions to this AX equals 0? Just based on what's on the screen right now, the answer is yes. that there is another vector, this purple thing, which when we multiply A by that purple vector becomes the zero vector, the green zero vector, if you like. So in this particular example, there are others. There are others for this A. And that's where the language of non-trivial comes in. When I say non-trivial solution to this system, that means other than the zero vector. Right? Is there anything besides the zero vector that when we multiply it by A, we get 0, 0? And in this example, the answer is yes, we at least have this vector. But then your group found at least several other examples of vectors that this matrix sends to 0, 0. Purple things that go to the green zero vector under this matrix A. Did you figure out what they all had in common?
The parametric vector solution, the direction vector, whatever that second part is, that's multiplied against t, was equal to the...
All right, so let me sort of copy down onto the screen here to wrap up today what you found. So when you solved the equation AX equals 0 in parametric vector form, you got x is equal to, let me make sure I have your, see where did I put your write-up? Here it is. The parametric vector form of your solution you got for that was the vector 5/2, 1, multiplied by t. So that was the parametric vector form of the, what we call, here's a $20 word for you, homogeneous equation. So if I say homogeneous equation, what I mean is that this right-hand side is 0. That's all I mean. So the homogeneous equation has parametric vector solution x equals 5/2, 1 multiplied by t. But then you also had the equation ax equals 1, negative 2. So a different right-hand side, but everything else about it was the same. And when you found your parametric vector solution of this equation, you got x equals, and you had a constant vector here, negative 1/2, 0. But then the second portion, where your parametric vector piece was, happened to be suspiciously similar. And that's crucial. That tells us something very important about why we might care about the homogeneous equation, why we might care about AX equals 0. Because that same solution to the homogeneous equation happens to show up in the solution set of other inhomogeneous equations. So inhomogeneous would just mean that my right-hand side is not 0. And there's a checkbox in this app that I didn't tell you about for precisely this reason, because it would have spoiled the surprise. But let's visualize what this looks like. So we have these two different solution sets, one to the homogeneous equation, one to the inhomogeneous equation, and they look awfully similar because they have this one piece that's repeated in both of them. So what do those solution sets look like as subsets of the domain, subsets of the purple xy plane up here? If I check the little labels checkbox, it'll show it to me. So I'm first going to arrange my image vector back to be 1, negative 2. 1, negative 2. There. Now let's check on labels. So here's what's going on. That over here on the left, I've got two lines, a light purple and a dark purple. The light purple line here is the solution set of the homogeneous equation. The homogeneous solution set. It's a straight line, solution set. It's a straight line that happens to pass through the origin. And not only that, the vector 5/2, 1 that you found a second ago, that vector is right there along our solution set line. So 5/2, 1 is that vector. Meanwhile, the solution set of this inhomogeneous equation is the stronger purple line that's right next to it. What do those two lines have in common? They have the same direction. What kind of lines are they? They're parallel. They have the same direction vector. So the inhomogeneous solution set looks just like the homogeneous solution set. The only difference is that it's moved a little bit. That you had this solution negative 1/2 comma 0. That's right here, by the way. That told us how we shifted our homogeneous solution set to get our inhomogeneous solution set. But the parallel nature of those two things is what's really I wanted to draw the most attention to today, to wrap up today. That knowing about the homogeneous solution set tells us about the inhomogeneous solution set. Inhomogeneous is parallel, it's just a parallel copy of the homogeneous solution set. The other thing that we can see on this diagram is over here on the right-hand side, and this was your group's question, when is it true that we have a consistent system? Well, we only have a consistent system if our green vector, our B vector, lies along, in this case, this line, which is sloping from top left to lower right. If we came up with an equation for this line, or actually better yet, let's just find a vector which is in this line. Notice that this happens to pass right through a lattice point right there, negative 2, 4. Where is negative 2, 4 in our matrix? It's first column. And so we had a consistent system because our vector, our B, actually lied in the same line as that column and as this column. Right? 5, negative 10 would be on this same line. It would just be further down off the screen where we can't see it. So we only get a consistent system for those green vectors that lie along that line. It has a name that I've sort of obscured here. It's called the column space of this matrix. But that's something we'll get into terminologically a little bit more next week. So what we can learn from playing around with this app is when we get a consistent system, we get a consistent system precisely because our B vector lies in the column space of this matrix. In other words, in this example, it's that line going from top left to bottom right. All of these are consistent systems. And when we have a consistent system to this matrix equation, the solution set is just a parallel copy of the solution set of the homogeneous equation AX equals 0. So that's what we can take away from all of this. And this applet right here, we're going to keep coming back to over the course of the next week or so as we continue to ask these questions. Is it consistent? And is the solution unique? And we have a little more perspective now than we had when we came in, I hope, this morning.